So derivatives of polynomial in exponential functions. All right. So the first derivative is the derivative of the constant functions. Right, for the constant functions, it's very simple here. So you have this right here is the function y equal to c, for c is any arbitrary constant. So consider constant functions. Y equal to c. Right. So back in pre-calculus, you learned that for the constant functions or the horizontal line, the slope of the line is equal to 0. Right? So it's a slope equal to 0. Right. So, right. And when we derive the derivative, is actually the limit of the slope of a tangent line. Right. So the slope in this case equal to 0. So for sure that the derivative of the constant function is equal to 0 as well. So you can have the derivative of y prime, or you can write c prime in this case is always equal to 0. So in fact, the derivative of any constant function is going to be equal to 0, right? So that's the very first formula about derivative that you're going to see. Derivative of a constant function is always equal to 0. So the derivative, so f prime, sorry, when f of x is equal to c, f prime of x is equal to 0. Then moving on to the second type of functions, that's the power functions. Then therefore you have the derivative of power functions. Or you can have this as called the power rule of derivative. For f of x equal to x, what is the derivative of the functions equal to? Lecture. Right. So f of x equal to x, the derivative is equal to 1. When f of x equal to x squared, the derivative is 2x. All right. So now that we can move on to the next example, which is the derivative of the cubic functions. Let's see what happened. All right. So determine the prime of x for f of x equal to x cubed using limit definitions of derivative. Right, so definitions of derivative is prime of x equal to limit as h approaches 0 of f of x plus h minus f of x altogether divided by h. All right. So you have limit as h approaches 0 of x plus h cube minus x cube divided by h. All right, so let's expand the numerator. You have x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed divided by h all together. All right, so for this, x cubed cancel out. Limit as h approaches 0 of 3x squared h plus 3x h squared plus h cubed divided by h. Now you can take h as the common factor on the numerator. 3x squared plus 3xh plus h cubed divided by h. So h simplify. All right, now you let h approach 0, you have 3x squared. So from the three functions, f of x equal to x, the derivative is equal to 1. F of x equal to x squared, the derivative should be equal to 2x. And when f of x is equal to x cubed, you have the first derivative is equal to 3x squared, right? So hopefully by looking at this, you kind of find the pattern out of this, right? And when I give you, let's say, f of x equal to x to the fourth, then derivative should be 4 times x cubed, right? So the power 4 bring down to become a constant multiple, and the power reduced by 1 degree. So now let's go crazy here a little bit, right? So you have f of x equal to x to the fifth power. Then the first derivative is, right, take the power, bring that to become a constant multiple. So 5 times x, and the power get reduced by 1 degree. So it's x to the fourth. Right. So for the power functions like this, you can deduce to a general formula, which is the power rule for derivative. So power rule. Right, so f of x equal to x to the power n, for n is any number, is f prime of x going to be n times x to the power n minus 1. For n is any number, no real number. Let's do some example here using this rule, the power rule. Differentiate the following functions. So you have f of x equal to, let's say, x to the 100. So using the power rule, you can write the first derivative is 100 times x to the 99. So if I give you f of x equal to 1 over x squared, what could you do? So this is the fractions, right? We don't do any fractions so far for derivative. But what you can do is you change these functions to a power functions, right? What I meant is that I'm going to rewrite this as x to the negative 2. Then you can just apply the power rule we just got earlier. So this one is negative 2 times x to the negative 2 minus 1. And therefore, this is 2 times x to the negative 3. Or if you want, you can rewrite this in terms of fractions. It's negative 2 over x cubed. What about if I give you f of x equal to square root of x? The first thing you can do is, this is the square root of radical, right? Change that to a power again, right? So radical x is x to the power 1/2. When you have power 1/2, you can use the power rule, which is 1/2 times x to the negative 1/2. Right. You can rearrange this function, so this derivative, so that you have a positive power. So I turn this into 1/2 times 1 over x to the 1/2. X to the 1/2 is square root, so I have 1 over 2 times square root of x. So the next example is f of x equal to cube root of x squared. Right, so now I have a rational exponent. Right. So try to turn this into a power functions as well. So the power is x to the 2/3. So the derivative is 2/3 times x to the power 2/3 minus 1, or 2/3 times x to the negative 1/3. Just like the previous problem, you can turn this to a positive power. So 1 over x to the 1/3, and 1/3 is cube root. Right? So you have 2 over 3 times cube root of x. So there, you're probably going to ask, so what is the plausible answer here to get the full credit, right? You know, you just stop right here, right? So I'm going to test you the knowledge of derivative of differentiations. If you stop right here, it's fine, right? Totally fine. You get 100% score. If you go all the way here, I'm gonna love this so much, right? Because it's a lot easier for me to look at. But certainly you don't have to. So if you stop right here at this step, that's good. If you stop right here at this step for the functions q root of x squared, I'm going to give you another function here, f of x equal to square root of x to the 13. Right, so once again, turn this into a power. So you have x to the 13 over 2. And the derivative should be 13 over 2 times x to the power of 13 over 2 minus 1. This is 13 over 2 times x to the 11/2. All right, so one last example on this family. So f of x equal to 1 over 4th root of x to the 3rd power. Right. Once again, try to turn this into a power functions. Right, so in the denominator, you can turn this into x to the power 3/4. Right. And once again, this is the fraction. You don't know how to differentiate a fraction, so turn that into a power. So this is x to the negative 3/4. Now you know how to differentiate this. So the first derivative is negative 3/4 times x to the negative 3/4 minus 1. This gives me negative 3/4 times x to the negative 7/4. Just leave it like that. That's okay as well. All right, so we look at power rule. We've done some example related to using power rule. Let's move on to the next formula. This is the constant multiple rule. So constant multiple rule. So if C is a constant and F is differentiable, then g of x is equal to c times f of x, implies that the first derivative is c times f prime of x. Right, so the constant c is multiplied with another functions. So when you take the derivative, you just take the derivative of the function and you leave the constant alone. Unlike the derivative of a constant itself, derivative of a constant by itself is equal to 0, but if the constant get multiplied with something else, then you have to use the constant multiple rule. Right, so that's it for that formula. Let's take a look at the example. So the example of find the derivatives. Find the derivative of the following functions. Right, so the first functions I'm going to give you is f of x equal to 3x to the 4th. So the first derivative is what? Right, so there is a constant multiple here, right? So 3 is the constant multiple. Just going to leave it like that. When I differentiate this, just going to differentiate x to the 4th. So 3 times 4 times x cubed. Right, the 3 is there because it's the constant multiple, so I'm not going to touch that, right? Just leave it alone. Then if you simplify it, you have 12x cubed. For the next questions, I'm going to use the Leibniz notations, right? So can you find the derivative of this? So negative 2 times t to the 39. Right, so d dt of negative 2 times t to the 39 means that take the derivative with respect to t for the function negative 2t to the 39. Right, so d dt means that differentiate of functions with respect to t. So ddt of -2t to the 39, right? So -2 is the constant multiple, so you don't touch that. Just leave it alone and just take the derivative of t to the 39. You can write like that. And ddt of t to the 39 is -2 times 39 times t to the power 39 minus 1. Well, this is what? -78 times t to the 38. Next questions, I'd like to do ddx of pi over the fifth root of x to the 8. So pi is the constant multiple. So I'm going to write pi out here and just going to apply the differentiations operations on the functions 1 over root 5 of x to the power 8. Right, so derivative of this function, you know how to do this by now, hopefully, right? Turn this into a power functions. This is pi times ddx of 1 over x to the power 8 over 5. And then this is equal to pi times ddx of x to the -8/5. So derivative of this is pi times -8 over 5 times x to the power a -8 over 5 minus 1. Well, I have -8 pi over 5 times x to the -13 over 5. So maybe like this. From the beginning, right? So if you would consider the constant function by itself, if you just take the derivative of a constant by itself with nothing attached to that, then yes, the derivative of that is equal to 0. But now, this is a different formula, different situations when you have a constant multiple, right? A constant get multiplied by something else, right? Therefore, you keep the constant and you just differentiate the function. All right. So go back to the example here. Pi is a constant multiple. So you leave pi alone. Don't do anything with that. And just take the derivative of this particular function. Let's move on to the next rule, which is the sum and difference rule. If f and g are both differentiable, then the derivative of a sum is the sum of the derivative. Derivative of a sum is the sum of derivatives. You can certainly do the same thing for the case of a difference. Right. The derivative of difference is the difference of derivatives. So another notations that I can use for the case of any case for that matter is use the Leibniz notations of ddx of f of x plus or minus g of x. Might just mean that take derivative of the sum or take derivative of the difference. That means derivative of the sum is the sum of derivatives. So example. So can you differentiate the following? So ddx of x to the 8 plus 12 x to the 5th power minus 6 plus 5. something like that, right? So there are additions, there are subtractions inside the parentheses. So once again, the derivative of the sum is the sum of the derivative, and the derivative of the difference of the derivative. So you can write this as d dx of x to the 8 plus d dx of 12 times x to the 5th power minus d dx of 6x plus d dx of 5. All right. So for d dx of x to the power 8, what I'm going to do is I'm going to use power rule right here. And I could obtain 8 times x to the 7, right? So 8 times x to the power 8 minus 1, so to get 7. So the next one, I use constant multiple first. Right, so constant multiple rule. This give me plus 12 times 5 times x to the 4th. Right, so I just take the derivative of x to the 5th power. And the next one, I also use the constant multiple rule. Right? And I get minus 6 times the derivative of x is just 1. Right? And for the last term, the derivative of a constant is 0. So I'm going to put 0 here just to indicate that the last derivative here is the constant functions. Right, so I apply the constant function rule. So that's why I get the derivative equal to 0. All right, so let's do another example here. So f of x equal to 4 minus 3 times square root of x. All right, so what is the first derivative here? Right, so the first derivative is for, right, so you want to find the derivative of that function, right? So derivative of difference of derivative, so derivative of 4 by itself, there's no variable attached to that, should be equal to 0. And then you subtract 3 times square root of x, take the derivative of that. This is the constant multiple. So let me write like this. So I'm not going to touch the 3, just leave the 3 by itself. And I want to find the derivative of square root of x. All right, so turn that square root of x into a power function. So I got negative 3 times x to the negative 1/2 prime. And then I can apply power rule right here. And I get this is negative 3 times negative 1/2 times x to the negative 1/2 minus 1. Simplify this, I get positive 3/2 times x to the negative 3/2. The applications of derivatives to calculate the slope of a tangent line, to calculate the instantaneous velocity of some, some object. So we will do some more of that. Before doing that, relations between position functions, velocity, and acceleration functions. So consider P of t to be the position function. V of t is the velocity function. And A of t is the acceleration function. V of t is equal to the derivative of P of t, or d dt of P of t, right? So the velocity is the derivative of the position functions, And the acceleration functions is the derivative of the velocity functions. Or it should be the second derivative of the position function. So that's the relation between position function, velocity functions, and acceleration function. All right, so let's take a look at the example here. The equations of motions of a particle is P of t equal to 2 times t cubed minus 5t squared plus 3t plus 4, where P is measured in centimeter and t is in second. T in seconds. Right, so part A, find derivative, or find the velocity, sorry, find the velocity as a function of t. So once again, the velocity is the first derivative of the position functions. So what you can do is you write v of t is equal to derivative of the position functions with respect to t, right? Because t is the variable in this case. Is equal to d dt of 2t cubed minus 5t squared plus 3t plus 4. All right. So what you can do is you do 2 times 3t squared minus 5 times 2t plus 3. So you simplify this and you should get 6t squared minus 10t plus 3, right? So I skip a couple of steps, so let me move this down a little bit. So between this line, right, this line and the next line, there should be a couple of more steps, but I skip it. Once again, the derivative of the sum is the sum of the derivative, yes, and derivative of the difference of derivative. Right. So you have derivative of 2t cubed minus d dt of 5t squared plus d dt of 3t plus d dt of 4. All right. So the first term, derivative of 2t cubed, constant multiple. Right? What is the derivative of t cubed? Right? You use power rule. Right? You have power rule here, 3 times t to the 3 minus 1, and then minus 5 times 2t to the 2 minus 1. Right? Then it's plus 3. Derivative of t is equal to 1, so that's why we got 3, only 3. Derivative of 4 by itself is 0. Right, so this is the velocity functions, right? Velocity, once again, is the derivative of the position functions, and the unit of this should be centimeter per second. So part B, find the acceleration functions of the particle. Then evaluate the accelerations of the particle after 2 seconds. All right. So once again, acceleration is the derivative of the velocity functions, right? Acceleration functions is d dt of v of t. Right, so this give me d dt of 6t squared minus 10t plus 3. Or I can write d dt of 6t squared minus d dt of 10t plus d dt of 3. D dt of 6t squared is 6 times 2 times t to the power 2 minus 1. and then minus 10 because derivative of t is equal to 1. And then the derivative of a constant by itself is 0, so that's what you get, right? And this, you simplify it, you should get 12t minus 10. All right, so this is the acceleration functions, and the accelerations, the unit of the acceleration is centimeter per second square. So acceleration is the derivative of the velocity. In other words, it's the instantaneous rate of change of the velocity. So another way to look at the acceleration is the instantaneous rate of change of the velocity. Now for the next part, you want to calculate the accelerations after 2 seconds, right? So the accelerations of the particle after 2 seconds is, so a of 2, right? So because in this case t equal to 2, so that's why a of 2 equal to 12 times 2 minus 10. You got 24 minus 10, which is 14. This is centimeter per second square. The next topic should be the derivative of exponential functions. There are two formulas. The first one is the f of x equal to e to the x. Then the derivative of e to the x is just e to the x. This is probably the easiest formula to remember. So this function is called the natural exponential functions. Natural exponential functions. There's a common or the generic exponential functions. I call this f of x equal to a to the power x for a is greater than 0 and a is different from 1. And the derivative of this is ln of a times a to the x. Before I do some example for derivative of exponential functions, I want to show you some graphs, some simulation, I could say, just to see the relations between the graph of the original function and the graph of the derivative functions, okay? There are two functions, f of x in blue and the slope of f of x. The slope of f of x, that means that derivative of f of x, right? There are two functions, the original functions up here and the derivative functions, right? So you know from our calculations earlier at the beginning of this lecture, we know that the derivative of any constant is equal to 0. So you can see right here, right? So if I move along the horizontal line on f of x, the cursor move along the x-axis to indicate that the value of the derivative is equal to 0. Now also from the power rule, you know that if the original function is equal to x, which is a linear function, right? The derivative has to be a constant, right? Let's see here, right? So the derivative of x is equal to 1, the derivative of 2x is equal to 2, right? The derivative of negative 3 is negative 3x is equal to negative 3. Also, now move on to the quadratic functions, right? X squared on the power x to the second degree. Derivative of x squared is equal to 2x, right? 2x is a linear function. So derivative of the quadratic functions is a linear function. Now derivative of a cubic functions, you're going to have 3x squared. Right? Derivative of x cubed is 3x squared. So you have derivative function is the quadratic function. Now I'm going to move to exponential functions, right? E to the x. Right, you can see the original function and the derivative function match exactly the same. So that's why the derivative of the original function e to the x is the same, is equal to e to the x. So once again, the derivative is the slope of the functions of the original function. So therefore, when you calculate the slope for e to the x, we could get that the derivative is going to be the same as the original function. All right, because of that simulations, right, of this formula, I could want to make a quick note here in terms of exponential functions, natural exponential functions. F of x equal to e to the x. Right. The slope of the tangent line to the curve y equal to e to the x is equal to the y coordinates of the points on y equal to the x. So that's why these derivative functions is equal to the original function. All right, so let's do some example now. So differentiate f of x equal to e to the x minus x. So the derivative of this should be e to the x minus x prime, or this is equal to e to the x minus x prime. Derivative of e to the x is e to the x. Derivative of x is equal to 1. So that's the derivative function. For b, I have this g of t equal to 2t. So this is exponential function. So you go back to the formula right here. The exponential function a to the x is equal to ln of a times a to the x. I go back to a little earlier. So the derivative of this function should be ln of 2 times 2 to the t. And that's it. Part c, g of x equal to 5 to the x plus x to the 5th power minus 5 times e to the x. All right. So the derivative of this is, right, 5, derivative of 5 to the x should be ln of 5 times 5 to the x plus derivative of x to the 5th power is 5 times x to the 4th. Then minus 5 times derivative of e to the x is just e to the x. So let's move on to the next example. F of x equal to 7 to the x minus 6 times q root of x plus 8 times e to the x. So derivative of this is 7 to the x prime minus 6 times x to the 1/3 prime plus 8 times e to the x prime. All right, so derivative of 7 to the x is ln of 7 times 7 to the x minus 6 times derivative of x to the 1/3 is 1/3 times x to the 1/3 minus 1 plus 8 times e to the x. This gives me ln of 7 times 7 to the x minus 2 times x to the negative 2/3 plus 8 times e to the x. So let's move on to the next example. Find the points on the curve y equal to x to the 4th minus 2x squared plus 4, where the tangent line is horizontal. So you want to find the point on the curve where the tangent line is horizontal. So let's analyze this, right? You have functions looking for points along the curve so that at those points you have a tangent line, the horizontal tangent line. So the horizontal tangent line gives you some information here, right? A line is horizontal when the slope is equal to 0. Now you have a slope, right? You want to find a point on this curve. What you can do is you matching the slope of the tangent line with the slope that you can obtain from the derivative of this function. You can find the derivative and you let the derivative equal to 0. Right, so what you can do in order to find the point is first, take the derivative of the functions. Y prime is equal to x to the fourth minus 2x squared plus 4 prime. This should give me x to the fourth prime minus 2 times x squared prime plus 4 prime. X to the fourth prime is 4 times x cubed. X squared prime is 2x, so 2 times 2 is 4x, then plus 0. So you set y prime equal to 0. Right, so set y prime equal to 0. We have 4x cubed minus 4x equal to 0. Right. And this is just regular solve equations, right? So 4x as the common factor, you're left with x squared minus 1 equal to 0. You can factor x squared minus 1. You get x minus 1 times x plus 1. So there should be 3 cases, right? X equal to 0, x equal to 1, x equal to negative 1. All right. So at x equal to 0, what is the point? What is y equal to? At x equal to 0, you can substitute x equal to 0 back into the original function. So you have y equal to 0 to the fourth minus 2 times 0 squared plus 4. And this give me equal to 4. So you have the first point is 0, 4. So at x equal to 1, you have y equal to 1 to the fourth minus 2 times 1 squared plus 4. This should give me 1 minus 2 plus 4 equal to 3. So you have the second point, which is 1, 3. All right, so when x equal to negative 1, you have the next point is negative 1, 3. So you say that at 0, 4, 1, 3, and negative 1, 3, the curve has horizontal tangent line. All right, so as you can see here in this graph, the red curve is the curve that we are working with. There are 3 points. At 3 points, you have horizontal tangent line. The first point is 0, 4 right here. Another point is 1, 3 right here. And another one is negative 1, 3. So hopefully you get some idea of what the curves look like, and how the horizontal tangent line going to pass through the curve.